Thank you.
I report on the work done in collaboration with Thomas Closet, Tristan McLaughlin, Rado Roiban, and Joe Minahan. And our motivation is to study the AdSxS correspondence, and in particular attempts to understand how does it work in details. So, according to the AdSxS correspondence, the rings of glue in supersymmetric Yang-Mills theory are described by strings in AdS5 crosses 5. Now, even if one looks at just comparing the spectra of the two theories, there is a certain puzzle, the resolution of which is not complete now. And it has to do with the fact that on one side, the system looks discrete, the spectrum looks as a spectrum of some discrete system, and it looks completely continuous on the other side. So the spectral problem of supersymmetric Yang-Mills theory can be reformulated as a problem of diagonalizing a spin Hamiltonian, which turns out to be integrable. This approach is very efficient for operators. Well, the states in super-Yang-Mills theory are conformal operators. We consider the large and limit, where we can look at single trace operators, and they can be identified with the states of a spin chain. The energies are scaling dimensions of these operators. And it is, this approach is efficient for operators that have many constituent fields, these B-main type operators. However, the Hamiltonian of this spin chain is not known beyond one loop. Well, it has sort of a block structure, and in certain blocks it's known to higher loops, but in general it's just, we only know it at order lambda, where lambda is the truth coupling of the Yang-Mills theory. However, for operators of this type which are built from one kind of scalar field with impurities inserted in between, a natural question to ask is what happens if we take two impurities together and then pull them apart again. So this is basically the question of how these impurities scatter on each other. And through a series of remarkable developments in the recent years, the exact S matrix for the scattering of impurities in the spin chain was found, exactly non-perturbatively in the truth coupling. So this is sort of paradoxical situation. We don't know the Hamiltonian of the system exactly, but we know the S matrix. On the string side, the situation is opposite. We know the sigma model Lagrangian. We can write down the Hamiltonian. It won't look particularly simple, but it's a well-defined two-dimensional quantum field theory, which is also integrable. And at the end, we expect that its spectrum is exactly equivalent to the spectrum of the spin chain. So it has to self-discretize at finite or at small values of the truth coupling. So how does this happen is not completely clear at the moment. Our goal was to study this theory perturbatively, just compute the S matrix to a few lowest orders in perturbation theory and compare it to the S matrix of the spin chain. So for that we need to fix some gauge, and anticipating that we will work in a physical gauge, like light cone gauge, we choose the coordinates in AdS5 cross 5 such that we pick up the time direction in AdS and an angle in S5, and then the rest will be the transverse coordinates. So there are 4 transverse directions in each of the AdSx5 and S5. We can choose the metric in this form. These are the global coordinates of AdS5 cross S5. And the sigma model, the bosonic part is basically determined by the metric. It is known how to couple fermions. And in total, this is a Green-Schwarz type coset sigma model with this symmetry group. Its coupling constant is inversely proportional to the curved coupling of Young-Mills theory. So if you take lambda large, this will be a classical limit of the sigma model. So the question I would like to answer is how to perturb away from this classical limit. Now, in quantizing this sigma model, one encounters certain technical difficulties which are actually well known. So because of the presence of Ramon-Ramon flux in the background, one has to use formulation of the theory which is manifestly supersymmetric in target space. So basically the Green-Schwarz formulation. And then standard methods of conformal field theory that are so efficient in other curved backgrounds do not work here. So there is no kinetic term for fermions. Currents do not factorize, so they are not holomorphic. So standard CFT doesn't seem to work. Let me expand a little bit on that. So because fermionic coordinates of the string are space-time spinors, the Dirac matrices are projections of 10-dimensional. 2-dimensional Dirac matrices are projections of 10-dimensional Dirac matrices and involve derivatives of the worldsheet, bosonic worldsheet coordinates. So if we expand around a point, these projections are 0, and we can't do perturbation theory because the kinetic term for fermions vanishes. So we have to introduce a non-trivial, time-dependent background for string coordinates. So we should expand near world line, not near point. Well, we will use the more or less the standard procedure to do that. We start with the BMN geodesic, the light-like geodesic on the sphere, around the big circle of the sphere, and fix the angle of momentum of the string. So of course, as any gauge fixing, it will break the global symmetries. And apparently the global symmetries of the sphere are broken to SO4, and the same is true for AdS5. And so SO4 is a product of 2SU2, so the unbroken bosonic subgroup is 4 copies of SU2 groups. If one takes into account supersymmetry, this is extended to 2 copies of SU2/2 supergroups. Now, very important observation originally due to Beiser is that this supersymmetry gets centrally extended with the central charge that's proportional, or actually it's a sign of the worldsheet momentum. The worldsheet coordinates, which are the fields of the 2-dimensional sigma model, are bifundamentals of this supergroup. So they have two SU2 indices. Okay, so there are these 4 transverse coordinates, which we can parameterize as 2 2x2 matrices. Time direction and angle will be used for gauge fixing. And basically we can put all the fields into a single multiplet of PSU22 squared. So to fix the gauge, we can do the following set of steps. So the first step, we can do first we choose the light cone direction in a certain way, and I will use the gauge that interpolates between the temporal gauge and the genuine light cone gauge. So this x plus direction is light like if a is equal to 1/2, and it coincides with time direction if a is 0. So a is 0 is temporal gauge, a 1/2 is the light cone gauge. And then we t-dualize the direction that's perpendicular to that. So because of the t-duality, the dual angular coordinate is not periodic anymore, it's quasi-periodic, with the period that is the angular, it's basically the angular momentum. And then starting from the Nambu action, we can impose the gauge condition, just the usual static gauge in the Nambu action, and after scaling by the angular momentum, we obtain this nice Lagrangian. This is just the bosonic part of it. So it looks like, I mean, it's a hopeless problem to solve it directly, but at least we can do perturbation theory. Now, an important point here is that after this rescaling, the Lagrangian doesn't depend on any parameters. So the coupling constant appears only in front of the action, so that the h bar of the sigma model is 2 pi r squared of lambda, and the kinematic variable, the angular momentum, only appears in the boundary conditions for the field, so the internal length of the string is j plus measured in the units of 1 over square root of lambda. Now on the spin chain side, the length is just j. So this 1 over square root of lambda plays dual role in the sigma model. First of all, it's the h bar. It counts the number of loops, and secondly, it's the latest spacing. So the length of the system is proportional to the length of the spin chain with this proportionality coefficient. Now it seems to be that this is only true at strong coupling, that the lattice spacing gets renormalized, so it's a non-trivial function of the Hood coupling. It would be very interesting to understand how it happens in details, but this is not what I'm going to do in this talk. So I will actually take the limit when the length is infinite. So there are no parameters, I mean, no dimensional sort of parameters at all, just the coupling constant. And then, okay, one can expand the action in interaction terms, and one encounters, so the free action is that of 8 massive bosons. So it's a massive theory, and it's integrable. So one can study scattering, just scattering metrics in this theory. The kinetic part of the action in this theory is Lorentz invariant. However, the interactions are not. So the time derivatives and spatial derivatives enter asymmetrically into the interaction Lagrangian. So the Lorentz invariance is broken by interactions. It's also gauge dependent, but okay, it's gauge dependent. And as expected, the light cone gauge simplifies things a little bit. Okay, so there are 16 massive states with relativistic dispersion relation. Because the interactions break relativistic invariance, we expect that the dispersion relation will get loop corrections. And in fact, we know what is the exact dispersion, what the exact dispersion relation is. So it contains this sine function, and it means that the first correction comes at 2 loops. The one thing that I will be able to show is that this 2-loop correction comes correctly from doing loop diagrams in the sigma model. Another thing one can calculate is the S matrix of the sigma model. And okay, so since the fields are in the bifundamental, the S matrix, the two-body S matrix carries 8 indices. So there are 2 indices for each particles, and it describes 2 incoming states, 2 outgoing states. So it has 8 indices. But now this theory is integrable, and in integrable theories, the S matrix is way more simpler than in generic two-dimensional field theory. In particular, the many-body S matrices are just products, so there are no genuine many-body interactions. The say 3 to 3 scattering matrix is a product of pairwise interactions between each of the 3 particles. There is no particle production, so 2 to n processes are forbidden kinematically. There is also a set of constraints known as Yang-Baxter equation on the S matrix that follows from the independence of rewriting 3-body S matrix in terms of 2-body S matrices. And this constraint is rather strong. So in particular, in theories like that where the fields are in the bifundamental and there are actually 2 symmetry groups, the S matrix should factorize. So the flavor, or so left flavor or color and color indices should scatter independently. So the S matrix must be a tensor product. And then just from SU4 invariants, the S matrix can be decomposed into several tensor structures. And remarkably, if one imposes supersymmetry constraint, as was shown by Bizart, the S matrix gets completely determined up to an overall phase. So it's just symmetries almost completely fix the S matrix. Now if you look at this S matrix, it's written in terms of some kinematic variables that contain signs and exponents and exponentials. And well, it looks more like the S matrix of a lattice system, which it certainly is at weak Hooft coupling. And it not at all looks like an S matrix of a 2-dimensional field theory, because of all the signs. But when lambda is large, we have to expand this signs, and so momentum is always accompanied by 1 over square root of lambda. So they are expanded in Taylor series, and as I will show, that this S matrix indeed arrives as to first few orders in perturbation theory. It indeed describes scattering in the 2-dimensional sigma model in the physical gauge. The gauge dependence is very mild, it only affects the phase. So now in the derivation of this S matrix, the way this supersymmetry acts was really important, and it's not completely standard. So usually, the S matrix acts, 2 to 2 S matrix acts in a 2-particle Hilbert space. So it scatters 2 particles, and the in-state contains 2 particles. So we need to understand how the symmetry generators act on 2 particles. Now usually it's enough to know how symmetry generators acts in a single particle Hilbert space, and then just by one can continue to multi-particle states basically using Leibniz rule. So it's like in this formula. So it first acts on the symmetry generator first acts on particle number 1, and then on particle number 2 independently. But it's not quite the case here. The supercharges act in a non-trivial way. So one has to accompany the supercharges by some phase factors that depend on the momentum of the particles being scattered. Now, on the spin chain, that arises pretty naturally because the supersymmetries change the length of the scale. So basically, the length of this of the spin chain. The length of the spin chain at tree level is the number of constituent fields, and supersymmetries obviously can change the number of constituent fields or the basic dimension of the operator. So the spin chain is dynamical, and therefore the action of supersymmetries contains translations by one side of the lattice, which are quite manifest here. So these are just translation generators by one side. Now, how does this arise in the sigma model where we don't have lattice structure? So this can be formalized mathematically as that there is a non-trivial Hopf algebra. So the extension of single particle symmetries to many body states is accomplished by a non-trivial coproduct. Now I can offer two explanations for this. So one explanation is based on the structure of supercurrents in the sigma model. Turns out that in these physical gauges, the supercurrents are non-local operators. So there is a part that's local in Worldsheet fields, but then it's accompanied by this exponential, and what's stand in the exponent is, its derivative is the translation generator. So it's an integral of some local field. Basically, this local field is one component of the energy momentum tensor. And then by contour manipulations, one can show that indeed this translation operator arises if one pulls this supercurrent through a local field. So if we say think of the S matrix and LSD terms, then the action of the symmetry generators on two body states will contain this non-trivial coproduct. Another explanation is based on giant magnons. So it was argued by Hoffman and Moldesena that the scattering states for parametrically large momentum are not really particles, they are solitons called giant magnons. So I'd like to put forward actually this is a conjecture that the giant magnons carry fractional fermion charge. So you know, in two-dimensional field theories, fermion charge need not be integer, and sometimes radiative corrections indeed induce fractional statistics for fermions. So if you assume that this happens for giant magnons, in principle that can be checked, then the coproduct follows just from Fermi statistics. So usually if we pull the supercharge through a fermion, we get this -1 to the F factor, and this, if F is fractional, this becomes the translation generator. Now, okay, so we can also compute the scattering matrix explicitly just from Feynman diagrams, and it's quite not trivial to see that it factorizes in these two symmetry factors. For instance, if we study the scattering of two scalars, they have all possible group structures appear, but then we need to project onto the SU2 squared tensors, and then we see that the S matrix essentially becomes factorized, so there are no cross terms between the two groups. So this is the outcome of explicit trivial calculations. And if one corrects the S matrix by certain phase that's not fixed by symmetries, about which you will hear in the next talk by Nicholas Beiser, then there is an exact complete agreement with the calculation in the sigma model. To go beyond the tree level is very hard because the Lagrangian is complicated. It's not Lorentz invariant, so one has to resort to certain limits. And one limit that's particularly useful is so-called near flat limit, when one considers what can be as close as possible to left moving sector in the sigma model, so that there is no holomorphic factorization. So left movers and right movers do interact, but if one considers a kinematic regime where left movers have much larger momenta, one can simplify the action a little bit so it doesn't contain interactions of larger than quartic degree. And okay, so then it's possible to show that this field theory is actually finite. It doesn't have any UV divergences. Then mass renormalization in this theory that arises from this sunrise diagram precisely recovers this factor that comes out from expanding the sign. Okay, so the S matrix can be, we computed it up to a two-loop order, and that precisely agrees with the non-perturbative proposal put forward by Weiser, Fernandez, Lopez, and Eden and Staudacher. So I'll stop here. Thank you.
Okay, thank you. Questions, please? Please.
Does the gauge dependence on A suggest maybe you're missing some ghosts in your almost Lycone gauge?
Well, this is a physical gauge, so
no, but physical gauge is just one choice for A. You were saying that you get some for any choice of A, it's physical.
It's always a physical. I mean, there are no transverse degrees of freedom.
So how did you get A? How do you explain the gauge dependence in A?
Excuse me, who stays in this office, in this room, will get the ticket to be before other people to get lunch? Special ticket. Okay, please continue.
Well, it is the S matrix that's gauge dependent. So S matrix has no physical meaning from the target space point of view. So what has physical meaning is the spectrum, and in the spectrum, this extra phase factor that's gauge dependent cancels against the gauge dependence of the string lengths. So the physical quantities are, of course, gauge independent.
More questions, please? Okay. If no questions, maybe I will ask you questions. In Sine-Gordon model, if you use the requirement of factorizations, you have DDD poles. What is the situation here with Besser S matrix?
Oh, its pole structure is well understood. So there are certain bound states. The elementary particles there can make an infinite set of bound states, and they appear as poles in this matrix. There are also some double poles that arise from thresholds, so its analytic structure is consistent with unitarity.
Thank you. Maybe some more questions? If not, let's thank the speaker again.
Okay.